Oh, well, yeah. I assume that the kids that are brought to Moment are already primed for prime. Got it, got it? Prime for prize. That's a good type. Prime for prize. Nice.
Oh, I see.
Oh, okay.
I will just come here and make sure.
Oop.
That's awesome. Yeah, so it says shows recording.
Okay.
Yeah, you can get them all sick, like.
I'll just stand, yes.
Sure.
So our next speaker is Deepak Bal, and he will talk about matchings and independent sets in random and hybrid hypergraphs.
All right. Thank you for organizing on pretty short. I didn't do anything for this. Kind of the opposite. But yeah, well, thanks everyone for coming. The streets are a mess today, but we made it. All right. So this is all joint work with Patrick Bennett from Western Michigan University, who I went to graduate school with and have been working with since then. Okay. So in a graph, what's a matching? Or actually really in a hypergraph too. Matching is a set of pairwise disjoint edges. So edges that don't overlap. And an independent set is a set of vertices that don't contain an entire edge. So if you look at the graph induced on those vertices, it's empty. There's no edges. Okay, so that definition will work for hypergraphs too. And we'll use nu for the maximum size of a matching, and we'll use alpha for the maximum size of an independent set. And the goal is to find large matchings and independent sets in certain graphs and hypergraphs. That's a standard problem goal you often have, right? Okay. So now this is going to be a lot about kind of random graphs and things like that. So let me talk about what models we'll use. The most classic model, binomial random graph, GNP. You have KNP or KN, complete graph on n vertices, and for each edge you flip a coin that comes up heads with probability p, and if it comes up heads, you keep the edge. Okay. And a random d-regular graph, which is more what we're going to care about in this talk, is the following. Take a graph is d-regular if every vertex has degree d, right? So you consider a bag of all the d-regular graphs on n vertices, and you reach in and you pull one out. And that's a random d-regular graph. Okay, uniform distribution on all the d-regular graphs on n labeled vertices. Okay. Hypergraph, similar. So a hypergraph is it's just a subset of the subsets of the vertices, but we care about in this talk k uniform hypergraphs. That's where each edge has size k. So two uniform hypergraphs are just graphs. And a hypergraph is d-regular if every vertex lies in exactly d edges. Okay, same as for graphs. And then we can define this uniformly random d-regular k uniform hypergraph on n. So again, that's called HKND. Sorry, I'm not very consistent with my hair. Okay, there's a big bag with all the d-regular k uniform hypergraphs, and you reach and you pull one out. And that's what that is. Okay? Yeah. And then you might say, well, how are you ever going to say anything about that? Well, I'll talk about that a little. Okay. Yeah, labeled. Yeah, vertex set labeled 1 through n. Yeah, because I'm not going to reduce by isomorphism or anything. All right. So for graphs, what's the history for? Okay. So in this talk, I want to talk about algorithms for finding large matchings and large independent sets in graphs and hypergraphs. Okay. So first, we'll start with matchings in graphs. And then I'm going to just talk about random graphs, right? In arbitrary graphs, matchings is actually solvable in polynomial time by Edmonds' Blossom algorithm from the 70s. So this is one of the problems that's actually in P. But still, I think the Blossom algorithm is like n cubed or something. So you might want a faster algorithm than that, right? Especially on a huge graph. So, okay, random greedy matching. What's the simplest matching algorithm you can think of? You have your graph, you take an arbitrary edge, and you say, I want this edge to be in the matching. So you put it in the matching, but then anything touching it has to go away. So you delete the endpoints of the matching edge, and thus all the edges incident to that edge, and then you arbitrarily pick more and more edges. You go around like that. But arbitrary is too vague, so let's instead pick a random edge at each step. So amongst all the remaining edges, I'm going to pick a uniformly random one and take it. So this is a natural thing you might try and do. And on random graphs with P constant, Tinhofer, I didn't put any years in here, but look at the paper if you want. There's a lot of it. This is like 80s, early 90s kind of stuff. Okay. In dense random graphs, that's GNP, where P is constant, like where you flip a fair coin. That was analyzed just kind of the expectation of the size of the ending matching. And then Dyer, Fries, and Piddle, it turns out that we care usually more about sparse random graphs. Those are graphs where P isn't constant. We just had a lot of the interesting stuff happens down there. Okay, when P is very, very small, or C over N. Because what does this mean now? If you look at Gn C over N, then the expected degree of a vertex is now C. So if you want a random graph where the expected degree of a vertex is 7, then you look at Gn 7 over N. All right, so Dyer, Fries, and Piddle analyzed this algorithm on sparse random graphs as well, and they said, well, it finds a pretty large matching, but not a maximum one. So they can prove the matching that gets output by the random greedy algorithm is not maximum. So it's bounded away from it by a little bit, depending on C. Yeah.
It's shown for GNCN that it's not maximal, as in also GNP. Is that known to be maximal or not maximal?
I think that's a little, that's a little different. When C tends to infinity, it asymptotically does become maximal. But for fixed small c, it's not.
Okay, thank you.
No problem. So then there's this simple tweak. Actually, this predates that, but don't worry about that. It's called the Karp-Sipser algorithm. And what it says is, okay, don't just choose completely random edges to add to your matching. If there's a vertex of degree 1, match it. Okay, so anytime there's a vertex of degree 1, match that. Okay, and then if there's no vertices of degree 1, pick a random edge. So it's just a small tweak, a degree prioritization tweak, right? And that simple tweak leads to a big performance change. So the algorithm finds an almost maximum matching on Gn C over N. So you add that one little thing. And by the way, this algorithm still runs in linear time or something, right? So you can track your degrees and gobble up these degree 1 vertices. So then that finds an almost maximum matching on Gn C over N. And in fact, there's a interesting thing that when C is less than E, it finds a maximum match. When C is bigger than E, it finds an almost maximum. It still does better than E. It's just a simple tweak. And then Bowman and Fries later analyzed on fixed degree sequence random graphs. So fix a degree sequence you like, and analyze the Karp-Sipser algorithm. And they gave a condition on the degree sequence when it outputs a almost maximum matching. And indeed, their work, if random regular graphs are fixed degree sequence graphs where you fix all the degrees to be the same, and their analysis applies to that. So they say that Karp-Sipser gives an almost perfect matching on random regular graphs. That's one consequence of what they did. Okay, and then there's another tweak on this, which you might say, okay, what is Karp-Sipser? Anytime there's a degree 1, you take it, you match it. But if there's no degree 1s, you take a uniformly random edge. But you might think, okay, maybe a stronger version of that would be if I'll just always take a vertex of minimum degree in the graph, whatever that might be, and match it in hopes that that'll do better. And then eventually, maybe degree 1s will show up. And this algorithm is called min-greedy. So it's just a slightly stronger version of Karp-Sipser, and Fries, Radcliffe, Suen analyzed this on random cubic graphs, which is random 3 regular graphs. Okay, and proved it finds an almost perfect matching there. Okay, all right. This was before Bowman and Fries, so I didn't put any years again. Okay. Well, what I should have said, questions? So I guess the point of all this is like, yes, you could find maximum matchings using Edmonds Blossom algorithm, but like, you know, when n is super duper huge, you don't want to do that. These are linear time algorithms that do very well. Okay. All right. Independent sets. Now this problem is actually hard. Well, you know, finding the largest independent set in graph, but there's still an obvious greedy algorithm you would try. Pick a random vertex and say, I want this in my independent set. And if you throw that in the independent set, well, then anything touching it isn't allowed to be there anymore. So you delete all those vertices and hence all the edges touching them. And then you keep going. This is how you prove like very basic bounds on the independence number of a graph, right? You analyze that greedy. A bound on the independence number in terms of the max degree comes from analyzing this where you take arbitrary vertices.
So you mean like a lower bound?
Yeah, lower bound. Yeah, because I'm trying to find big ones. Yeah. Like the standard proof that alpha is bigger than n over delta plus 1 is just basically analyze this algorithm for arbitrary choices. Does that make sense? Every stage of the algorithm deletes at most delta plus 1 vertices. So continue in this way.
Is this how you get the lower bound with the for general degree as a sum of 1 over d plus degree plus 1?
Right. Yes, exactly. That thing. Yeah. Okay. Now instead, I should read my slides. Now choose a uniformly random available vertex and add that to your independent set. So that's called, in chemistry and physics, I guess that's called random sequential adsorption. Okay. Anyways, so this natural algorithm was analyzed on GNP by Grimmett and McDiarmid and Bolobash and Erdős, and on random D regular graphs by Wormald. And then also on regular graphs of high girth. So what's the girth of a graph? It's the length of the shortest cycle. Right? The length of the shortest cycle. Okay? So if a graph has high girth, then it has no short cycles. And what is that? What's a consequence of that? If you look at any vertex and you kind of expand outwards, what do you see? A tree. Okay, good. That's the point. Locally tree-like is high girth. Okay. So Pippinger, Lauer and Wormald, and Gomarnik and Goldberg, kind of building off of this, analyze this for regular graphs of high girth. Actually, this is I remember when I was first like looking into all this. This work is kind of like lost. No, we're in the paper we wrote about this. Like we're the first people to cite this since. Was written. Lauer and Wormald didn't know that Pippinger did it. It's just what sometimes this happens. People prove something, and then 20 years later, people prove it again and didn't know that they did. So, yeah. Anyways, it's one of those stories. Okay, but then again, instead of just picking uniformly random vertices, maybe you want to be a little smarter. So what do? Well, I don't know if it's smart or not, but. Well, what's the point? Every time you like pick a vertex, every time you add one of these vertices to your independent set, you have to delete all of its neighbors, right? Which somehow is making this algorithm last for a shorter amount of time, right? You want the algorithm to last a long time because you're adding a vertex to the independent set at every step. So how do you make it last a long time? Well, you say, well, I want to delete as little as possible every time. Okay. I'll pick a vertex of minimum degree. This only has a few neighbors. So when I delete it and its neighbors, I'm deleting a little bit. So hopefully this will make the algorithm last longer and I'll get a bigger independent set. Does that make sense? So this is called min greedy, same name as the matching algorithm, because it's the same thing. Same idea, right? You prioritize based on minimum degree. So Fries and Swen analyzed this on random cubic graphs and were able to come up with an analytic formula or like a number for how long the algorithm lasts when you do this. And they proved that. I didn't say that. It's like 0.43 something. Okay. All right. Cool. And then Wormald analyzed it on GNR in general with R greater than or equal to 3 and gave numerical lower bounds on the independence numbers. So basically, they were able to analyze this and get a number. Once you go to R equals 4 or larger, it's complicated. So maybe you just do something in Maple and get a number and say, okay. All right. Which is what the rest of this talk was about.
So delete it and its neighbors. You mean delete its neighbors, right?
I guess I want to delete it and its neighbors, but then I want to mark it as say you're in the independent set.
Oh, okay.
Yeah. You're in the independent set,
Yeah.
and I'm remove, and then there's some graph that's left over, and now I iterate it. Okay. Other questions? All right. But lesson: prioritizing small degree vertices creates larger matching. Yeah. Okay. Hypergraphs. So you understand there's two like the story so far is always random choices, slightly smarter random choices, random choices, slightly smarter random choices, right? That's what I did for both things. So of course, for hypergraphs, there's the random choices version. So I'm trying to build a large matching. At each stage, I take a uniformly random edge, put it in the matching. Uniformly random edge, put it in the matching, and delete whatever I have to. Same thing for independent sets. Uniformly random vertex, put it in the independent set, delete whatever I have to. Yeah. So on random K uniform D regular hypergraphs, Bennett and Patrick and I analyzed this. Well, anyway, we put this paper on the archive in 2016 and it got published in 2023. But if you look at version 1 on the archive, it's very different than what got published. And the reason is, at first we just did it for regular hypergraphs with fixed D, and we only did matching. That's it. And then nobody wanted to publish that. So we're like, okay, let's add the independent process. And nobody wanted to publish that. So then we're like, okay, let's do it for fixed degree sequences. And let's let the degree sequences tend to infinity. Okay, we had to make it a lot better. And then we had to connect it to a bunch of other work. You know, in the intervening years, people published stuff that was relevant. And then we had to be like, well, our stuff is actually, you know, it's the same as what they did. And we had to keep updating. But eventually it was good enough to get published. Okay, fine. But yeah, the ending paper is actually good, I think. All right, so remember, this is random D regular K uniform hypergraphs. Nie and Verstraat analyzed this process, the random greedy independent set process, on regular high girth hypergraphs. Okay, and the number they get is the same number that we get. Is that okay? So like, meaning they find that if you analyze this on regular high girth hypergraphs, you get some independent set of a certain size, and it's the same number that we got in our paper. Okay, great. We show that we show that it is the same number in our paper. Okay, so then what do I want to talk about in this talk? Is the degree prioritized versions of these algorithms for hypergraphs. Okay, so following the same story, but filling in that missing piece, degree prioritized hypergraphs. Okay, so let me describe the algorithms, even though you know what they are. You prioritize based on degrees. Okay, so matching, but now we're in a hypergraph, so the edges have size 3 or something. They're blobs instead of just lines, right? So, but there's still a notion of degree. So you start with, so what is the degree greedy matching algorithm in a hypergraph? You take a vertex of minimum degree, pick a random edge that it's in. It has, you know, maybe 2 edges that it's in. Pick a random one of those, and that's going to be your matching edge. Okay? And then when you add that to the matching, you have to delete everything you have to delete. Does that make sense? Okay. I hope so. Questions? All right. Local picture. Pick a vertex of minimum degree. Pick one of the edges that it's in. That's the chosen edge that you're going to add to the matching. And then you're going to delete that edge and all the vertices in it, which then deletes all the edges that are touching those vertices, right? So there's a lot of deletions that happen at every step, but delete the vertices of E and all its edges. Okay? Good.
We
Yes.
choose, our minimum degree, and then the edge that we choose, is that at random?
Yes, amongst the neighbors. So if it has 7 neighbors, of those 7, you pick a random one. And that's the one you add to the matching.
Is
Yeah,
this question all the time for hypergraphs?
yeah,
Is it so-
linear time algorithm.
No.
Oh, no. And I think you talked about it. 3-dimensional matching is
Oh, okay.
NP or. So I should have mentioned that. Matching for graphs, easy. Matching for hypergraphs, not easy. Once you go to 3 uniform and above, the matching problem is not polynomial time anymore. Independent set is always hard. Graphs or hypergraphs. Okay? And now I'm going to show you a picture.
Deepak, can I
Yes.
quick question? So with graphs, it makes sense to choose min degree vertex.
Yeah.
But for hypergraphs, would it make more sense to like use the degree of the edge somehow? Like,
Yeah. It would, wouldn't it?
Yeah.
Well, then we talk about. So basically what we say is, you're probably thinking there's a better algorithm that should do better. And we're like, yes, but it's just more complicated and it gives such a smaller gain that maybe it's not worth us writing about. Okay, but you're right. Because somehow for every edge, you should look at, if I pick this edge, how many deletions would I be making? That's what I should be trying to prioritize. You're right. And so this doesn't feel like the optimal algorithm, but okay. Yeah. Okay. Other questions? Good point, though.
Jim, it's Blossom algorithm for hypergraph.
Well, I think you can try, but it won't work because it's NP complete. The
No,
problem.
Blossom,
But the Blossom algorithm. So I don't know.
maybe exponential
Right. Yeah, probably. Yeah, I guess. I really
for some kinds of.
yeah, that's a good question. I don't know what happens if you try and do that. You know, there's all these different notions of cycle. I know that that's about like, right, odd cycles with the thing coming off of it. So I don't know what, how that works in hypergraph. No clue at all. Okay. Other questions? Okay. Now I'll show you a picture. Okay, so I'm matching one random run, so 10,000 vertices, 3 uniform, and 5 regular. And it returned a matching with 2,978 edges. Okay, now what is this picture you're looking at? It's, okay, so you started with all degree 5 vertices, right? So at the beginning of the process, the proportion of degree 5 vertices is everything, and the proportion of everything else is 0. And as the algorithm progresses, these things change. So you start processing edges, and the number of degree 5 vertices can only go down, right? You never are creating more of them, right? But at the same time, degree 4s start going up when you start processing edges, right? And then those are that's the min degree, becomes degree 4, so you're processing those for a while, right? And then you start processing degree 3s, and when those start coming up, you start taking those more and more often, right? So you see this picture. And look, it's a little jagged because this is I took a random graph. I took a random 5 regular 3 uniform graph on 10,002 vertices, and I ran the algorithm. And then I output what happened. But you might look at these and be like, but those curves, they look so nice. You know, like they look so smooth. Like, yeah, that's what this is about, basically. Okay. All right, we'll come back to this. Okay. Good. Independent set. Oh, by the way, this is great use of AI. I added this slide at 11 p.m. yesterday because I just went and I said, go to the hypergraph, do a 10,002 vertices, and give me the Python code to run the algorithm. Okay, now give me the code to track the degrees and make it a plot. And it just does it in 1 minute. And then I'm like, okay, I'll put this in the slides. Okay. What's that?
Are they by them?
Those functions?
I mean, those graphs there. What's the distribution code?
No, well, I'll come back to that, I guess. Like, what are those things? I'll come back to that. Okay, now that was matching. Here's independent set. And you know, if I had started this at 10 p.m. instead of 11, I would have had a picture for this one too. But no, really, but I can do it at the end of the talk. Oh, we got my independent set, and it'll do it. And then we got
And we
the
think
picture.
it's right.
I mean, I have reason to believe this is right. Because it matches with something that's coming up in 2 slides, right? Okay, good. Right, so hypergraph min greedy algorithm, you pick a random vertex of minimum degree, or you pick a vertex of minimum degree, and you say, I want to add you to the thing. And of course, you might think of a better one. Well, why don't you pick a vertex that's going to cause the fewest deletions? Yeah, you're right. But just a little more complicated. Okay, but okay. So do I need to talk about this much? Well, actually, I do need to talk about this because this last step is annoying. Because to delete every vertex v prime such that if you added that to v prime, it would make an edge. So how am I actually going to analyze this? Well, there's another way to view the independent set degree greedy algorithm, and that's like, see, okay, with independent sets, if I have an edge of size 4, I'm allowed to have 3 out of those 4 edges in my independent set because those don't induce that full edge, right? And so I don't just want to like get rid of these edges as they come up. It's like, well, I'm still allowed to keep taking vertices out of these edges, you know, as they come. And this might give you another idea for an algorithm, like when you pick an edge, take all but one of the vertices from it and add those. And so there's all sorts of algorithms you can come up with. Every time you come up with one of those algorithms, ask AI to code it up and see whether it does better than the one I'm talking about. And if it does consistently, then maybe it's worth analyzing. Does that make sense? This is really what it's about, I guess. I don't know. Okay. So now when I add a vertex to the independent set, I'm not going to like delete that edge. I'm just going to shrink the edge by 1 because I still want to keep it around. I might want to take some of those remaining vertices out of that edge. But when is it a problem? When an edge gets shrunk to size 1, that means I can't take that vertex anymore. Because it got shrunk to size 1 because every other vertex in that edge was taken. So if an edge gets shrunk to size 1, then I'll delete it. Then I'll delete that vertex and any edge touching it. So here's a bad picture of this. So I take a vertex of min degree and I want to add it to my independent set. So I don't delete everything containing it. I shrink all the edges. So there's 2 edges containing it. I shrink them, right? And then I say, oh, well, now this thing got shrunk to size 1, which means every other vertex in whatever this original edge was has been taken and added to the independent set. That's how that thing got shrunk to 1. And so I'm going to delete that vertex because I definitely don't want to have that on the table anymore. So I delete that, it goes away, and any edges containing that vertex go away. That's not a bad thing. That's just I don't have to care about those edges anymore. Those edges are already safe because I'm never going to take all the. Okay. All right. Okay, so here's a main theorem. And it's funny. But for fixed K and D, the degree greedy algorithms give you some constants that I guess you can compute with enough time on Maple, such that with high probability, a random K uniform D regular hypergraph, and also every sufficiently high girth K uniform D regular hypergraph has a matching of size at least this and an independent set of size at least this. So this is a with high probability statement for the random ones, but a deterministic every sufficiently high girth hypergraph has this statement for the high girth ones, okay? And I'll talk about how that's possible. And you get some numbers. You can't stare. Let me do the next slide because okay, so just showing you that random on a 3 uniform D, this is the case we were looking at. 3 uniform D regular. Random greedy gives you a matching of size this. Degree greedy matching gives you this size. And the best you could ever hope for is this. So, you know, it split the difference. It did better. Yeah. So it improved it. Okay. And similarly, for the other cases. Okay, everything in the table is better than if you looked at a random greedy table and you looked at that table. It's just strictly better. It does better. Okay, I guess that's the point. And then here's independent set. You can see it takes everything and increases it. And now somebody's going to say, "Whoa, but you got all the way up to the other round. How'd you do that?" Okay, there's this kind of a stupid reason for that, which I could talk about at the end if I have time. Okay, has to do with what is this? This is a 3 uniform, 2 regular hypergraph. 2 regular. Now in graphs, 2 regular hypergraph or 2 regular graphs are just, disjoint cycles. In hypergraphs, it's not that, it's a little more something, but it's still, there's a reason that this happened. Okay. All right. But I mean, I guess maybe the main, it's nice that this also applies to the high girth ones, because somehow people maybe care about that more than the random regular hypergraphs. Okay. That's it. So what do we use to prove these things? It's called the differential equations method. Okay, so let me tell you how the standard method works. There's a lot of things here. I could have made them reveal one at a time, but instead I'll just overwhelm you like this. Choose some variables you'd like to track throughout the process. You're running some algorithm. Choose some things you'd like to track. So in this case, like, how many vertices are left of degree 4? How many vertices are left of degree 3? Does that sound familiar? That in that picture I showed you, that's exactly the stuff. So that's the things I'd be trying to track. How many vertices of degree j are there left at time step I? That you say you want to track those variables. Okay, then you do this part. Compute the expected 1-step change at time step I. So suppose you're at time step I of the algorithm, and you get to assume that you know how many vertices of degree 5 and 4 and 3 and 2 and 1 there are. And you do 1 step of the algorithm. So you pick a vertex of minimum degree and you pick a random edge in it, remove it, and you talk about all the deletions, right? That's called the expected 1-step change. If you can somehow say for each of these things, well, okay, if there were this many degree 4 vertices before, then after 1 step, I expect it to go down or up by this much. That's what this is saying. Somehow, if you can do that, then maybe you're okay. Or I don't know. Now what you do is you take those and you rescale them. So remember, I is like, it's going to run, like this process is going to run as many edges as you're going to add to the matching, or as many vertices as you're going to add to the independent set. That's how long the process is going to run. Scale it so that just scale everything by n, the variables, okay? Now, if you look at this thing and you scale everything by n, then it's like, and you call that t, and it says t plus a little bit minus, so f of t plus epsilon minus f of t. It's starting to sound like a derivative, right? Okay, so after scaling these things, you call it, in the scaled version, call it lowercase y. After you scale it, this thing is a derivative of the yj, right? Because now, like, 1 over n is like your epsilon in a derivative, right? Okay. So then you get a system of differential equations that depend, so like, how much is the degree 3 is going to change? Well, that's going to depend on how many degree 1s, 2s, 3s, 4s, and 5s there are. Really just 4s and 5s and 3s, right? But like that change is going to depend on that. So you get a system of differential equations, and then you solve the system analytically or numerically. So let me just tell you, like, sometimes you can solve it analytically, and then you're very happy. So remember, Fries and Suen got that log of 6 log of whatever number that was, they were able to get that number because they could solve some system analytically. And then I said Wormald got numerical results. Well, when you go to higher degrees, it's kind of hopeless. Like the system's too complicated.
And they were all using this method.
Yes.
That's really cool.
So this method, differential, I should really have called it Wormald's differential equation method. Although, so the person who really popularized this is Nick Wormald, and he has some surveys about this where he gives a bunch of applications, including a lot of the stuff I'm talking. Okay. And he has multiple papers that are very useful because you can just use them as black boxes. All right. So yeah, anytime you're trying to track a process and you can write down the expected one-step changes, you get a system of ODEs. And then you solve the system. Okay, and what Wormald's theorems say is that the thing you would hope, like, so what is this? If you look at this, this is called the expected trajectory of the variables, right? So when I get that, say I solve that system numerically, that's just saying the expectation, the expected number of degree threes looks like this, right? But that doesn't tell you that if I take a run of 10,000 on 10,000 vertices and I run it, it's going to look anything like that, right? Maybe the variance is really big and like, it goes all crazy or something. I don't know. Well, Wormald says you do know. Okay, there's a bunch of technical assumptions you need on these one-step changes, but if everything's nice enough and you can check it, then you can say that, in fact, the unscaled versions stay close to their expected trajectories plus a small error. And as long as you can kind of, yeah, you're good. You're good, okay? So it's saying, so in other words, when I showed you that nice picture, this is what, see how it's like a little jagged. So what Wormald said, if I solve the expected trajectories, it would be some smooth curves that look like this. And these little jagged, what Wormald's theorem says is that these little jagged guys are never going to go too far. With high probability, these jagged guys won't go too far from the smooth ones. Okay? So that's how I knew this was going to look like this. It wasn't going to mess up. I could just do one random, I didn't run it, 100 times till I got one that looked good. I just ran it once and I put it in here. I knew it was going to work good unless I won the lottery or lost the lottery, whatever it is. Like for this to look bad, something would have to go really, really wrong. Does that make sense? So let me just show you what one of these expected. So what I'm doing now is the expected one-step change in vertices of degree J at time step I. Okay, I wrote this up just to show you what it looks like. You don't have to, you're not going to absorb this, but how does one think about these things? Well, say I'm trying to track how much do the degree J vertices change at time step I. And well, let's condition on that the minimum degree at time step I is R. So I'm processing a vertex of degree R, right? In which case, when I remove that vertex and the edge containing it, I'm definitely going to lose that. So suppose I'm tracking degree R vertices, then I'm definitely going to lose the one that I just processed, right? What does this term deal with? Well, this says you're going to lose these k-1 other vertices. Now, what degree do they have? Well, that's given by this expression, JYJ over, so that, okay, you don't have to read all this. But the point is, you can write down some probabilities that represent the probability that when you look at a vertex that's the neighbor of this thing, that it's going to have degree, 5 or 6 or something. And keep in mind, all this works because I'm, say, tracking all the vertices of degree J. So I know them at time step I. I know how many degree 3s there are at time step I, right? And so to go one step further, I can use that information to do this, okay? So this is how the expected one-step changes look. And now I'm saying, if you scale all this, this is little yj prime, where this is little yj and this is little yj. So you can imagine this system of differential equations is very ugly. And that's why we didn't solve it analytically. But I will say that in that paper that got published in 2023, for ordinary random greedy, we did solve the system analytically. Okay, we were able to find out, we were able to track these things and figure out when the process ended and get an actual expression for it, okay? But once you put in the degree prioritization, this thing's too ugly. And what made it so complicated? It's this minimum degree thing. Because the type of step in the ordinary random greedy thing, the type of step you take is the same every time. You pick a random edge and you take it. Pick a random edge, you take it. But what's different here, the current minimum degree determines the type of step you take. Does that make sense? Which then determines what one step change you have to apply. You know, so like on the previous slide, this was like given that the minimum degree is R. But like at any stage of the process, the minimum degree could be any of those things, and you don't know which one it is. But that complicates things. Okay, so I'll just say at the first step of this process, the min degree is D. You take an edge and the minimum degree becomes D minus 1. And for the next bunch of steps, the minimum degree is going to be D minus 1. But then eventually degree D minus 2 vertices begin to appear. And you say, oh, degree D minus 2 appeared. I'll process that one. And then it's gone. And the min degree goes back to D minus 1. And you process those until another D minus 2 appears. And you process that. But then what happens is like those D minus 2s are trying to, you're suppressing them by processing them all the time, but they're trying to build up, you know, because you're mostly processing degree D minus 1s. And every time you remove those, every time you hit one of those, it creates some D minus 2s, you know? And so those are trying to come up, but you're keeping them down for a while, but eventually you lose the battle and they start coming up. Okay, so once they start coming up, once you can't keep the degree 2s down anymore and they start becoming big, that's going to be the beginning of phase 2. So all that stuff I was describing before is phase 1, when you were able to suppress the D minus 2s, right? Then phase 2 is when you're mostly taking care of degree D minus 2s, but D minus 3s are popping up and you take care of them as they arrive, but then eventually they start accumulating. And that's the end of phase 2, when they start accumulating, okay, etc. Let me go back to well, maybe I won't, and so on. In phase P, you spend your time processing vertices, blah, 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 blah. Okay, but like I said, you know, in phase P, I'm processing vertices of degree D minus P and D minus P minus 1 in some proportion. And that proportion is changing as the process moves along. So how do you deal with all this? You blend the one-step changes according to the proportions at which you're taking these two steps. And that proportion is also the solution to another differential equation. Okay, so the system just becomes more complicated. But Wormald tells us that this blending works. Praying hands emoji. Okay, Wormald did it. Okay. So what I'm saying is that the differential equation system is a bit of a mess, but Wormald says, okay, you can do it. It works. And I'll just say, okay, look at this. This is the solution, the Maple-derived solutions of the analytical, you know, that system of ODEs with the blending of steps. It looks like this. See how these are nice smooth curves? And what does it look exactly like? That. Okay? So that's the point. And the vertical lines mark the end of the phases. Okay? So this is the really, I mean, I remember when I was in grad school and when I first did a simulation and I looked, I was like, this is amazing. I don't know why I thought, I guess I just didn't know what, you know, with high probability meant or something, or I didn't know what little o of 1 meant when you scaled it. But like, once you see that, I don't know, it's just beautiful, right? That you could take a big old random graph and do something random to it, and it just does the same thing every time. You know? Not the same thing. You could say what happens. It's amazing. Yeah, okay. So anyways, all right. Oh, by the way, and you know, so I'll just say getting Maple to output this is hard because you have to deal with blending of steps and then this and that, you know, it's annoying. But getting Python to output this is super easy. I just said to the ad, run the algorithm. The whole point is that it takes work to do this part. You know, you can code this up, but it doesn't tell you anything concrete. But once you've done this, Wormald says, well, whenever this process ends, that's how big the matching is. That kind of thing. Okay, makes sense? All right. So now let me do 3 viewpoints of hypergraphs. So remember, we've been talking about hypergraphs. This would be like 4 uniform, 3 regular, right? Okay. So if I have a hypergraph, there's something you can make called the bipartite incidence graph. And what's that? You make one side to represent the vertices and you make one side to represent the edges. Okay. And then what do? For every, so this is an ordinary bipartite graph. And for every vertex, you just say, what edges are you in? And for every edge, you say, what vertices do you contain? And you see this is a bipartite biregular graph, right? On this side, it's KD regular, because every vertex is in D edges. And on this side, it's K regular, because every edge contains K vertices. Okay, so it's a biregular bipartite graph. Okay, and now, I said you might be asking, how could you ever say anything about random regular graphs or random regular hypergraphs? And that's where this thing comes in, the pairing model. So this is almost like a weakening of that, not a weakening of this, but just now imagine blow each of these things up. So this thing has degree 3, just replace it with 3 vertices. This thing has degree 4, replace it with 4 vertices. Call those configuration points. So in here, this is called the pairing model. On one side, you have vertex points, okay? N parts of size D. So there's ND total vertex points. And then on this side, you have ND over K parts of size K. These are like the edge points. And what do you do now? Between these two sets, you just put a matching. You put a uniformly random matching, and now you can imagine going this way, right? So put a uniformly random matching on these points, collapse every one of these sets and collapse every one of these sets, you get one of these. Well, of course, there might be overlaps and things. You might get a multi-graph. Ignore that for a second, right? And then what do you do? Once you have one of these, you can get a hypergraph. So how do I analyze random regular hypergraphs? I use this thing. Okay. So the pairing model is used for the analysis of algorithms on random regular hypergraphs. And the nice thing about it is that at each step, I just reveal the parts of the pairing that I need to do that step. And I get to assume everything that's unrevealed is still uniformly random. So the way I'm able to analyze any of this is by revealing the randomness of the random graph a little bit at a time. Constant portions of the randomness are revealed at each step, and that allows me to compute the expected one-step changes conditional on what I've seen so far. Okay, now let me get to the high girth part. Local deletion algorithm. What is that? So a graph algorithm to build a desired object A is a local deletion algorithm if at each stage it selects some vertices, explores the neighborhoods up to some depth, inserts some of the stuff it explored into the desired object, and then deletes the explored stuff. Okay, that's called a local deletion algorithm. And I'll just say that the algorithms I described can be interpreted as local deletion algorithms on the middle thing on the bipart. Remember, this is just a graph. The algorithms I described can be interpreted as local deletion algorithms on here. Okay, good. Where am I? Yes. What am I doing? Yeah, no, here's just describing how the matching algorithm looks like. I reinterpreted the matching algorithm on bipartite incidence graph. Okay. So what is the thing that Hoppen and Wormald proved? This is the basis of whatever we did. Okay. After approximately 100 definitions, lemmas, and technical assumptions, and this is only kind of a joke, they get the following theorem that local deletion algorithms have asymptotically the same performance on random d-regular graphs and sufficiently high girth d-regular graphs. Okay, so it's really, okay, the paper's long and technical and the definitions are multiple pages, like one definition. The definition of local deletion algorithm takes like 2 pages. Okay, but it's still an amazing thing. So what it says is that if you want to know a result that holds for high girth regular graphs, and you know how to analyze it on random regular graphs, you're good. That's amazing, because you would think it would go the other way somehow. Somehow you'd think if you could analyze something on high girth graphs, then you could use the fact that like random regular graphs don't have many cycles to say it goes up. But this is saying the pairing model is so nice, maybe you want to use that, and then you get to go the other way. And that's really great. in my opinion. Okay, so Hoppen and Wormald did all this work. And so what we needed to do was show that this theorem and all of its stuff doesn't just apply to D-regular graphs, but DK biregular bipartite graphs. Okay, so it's just some minor little, making sure that in these 100 definitions and lemmas and technical assumptions, if you replace D-regular with DK biregular bipartite graph, it all still works. And okay, it does. And we asked Hoppen and Wormald, look, does this works, right? They're like, yeah. So I mean, it's not. It really is.
So you went through the 100.
We went through it. We went through it. We did not write it all down because it would be plagiarism. It'd be just copy and pasting. There's no way around their technical definitions, right? Like we're not going to redo all of it. We just said what you have to change, what definitions have to change, how you alter them, and then everything goes through. So the paper is kind of weird because we just kind of sketch what you need to change from their paper to make DK biregular bipartite graphs work. But once you have that, then you have, okay. When I talk about high girth hypergraphs, I mean no short Burge cycles. And I'll just say that what that is, like, in this bipartite incidence graph, it's ordinary girth in that graph. Okay. And I'm running out of time, so I'll just keep going. So what we get then is the transfer algorithm for hypergraphs. So it's the same theorem that they had, but now for K uniform D-regular hypergraphs. If you have a local algorithm on random ones, then you get the high girth result. Okay, good. Open questions. Come up with better algorithms. Sure. So can stronger local algorithms improve the constants? Yes, but to what extent? I don't know. Well, some people know some things. Okay, so recently Gawan and Wang showed that for large D, no local algorithm can find an asymptotically maximum independent set in random hypergraphs. Okay, so but we don't know whether the same is true for matchings. Okay. Whether it's true that no local algorithm can find an almost perfect matching if D is big enough, just in terms of K. Okay, so what's that? It's, well, let me just say this. So, and the other question is, do high girth K uniform D regular hypergraphs have almost perfect matchings? So this is true for graphs. So high girth K uniform D regular hypergraphs have almost perfect matchings. And random D regular hypergraphs have perfect matchings with high probability when D is sufficiently large in terms of K. And that's proved by the second moment method. So now basically what we're asking is, if a local algorithm could find these almost perfect matchings, then you could use our transfer result to prove it for high girths. But it still might be true for high girths even without a local algorithm proof. That's the question. Okay, so if if local algorithms can't find these things, then you need another way.
By local, you mean the same as local deletion?
Yeah,
Okay.
yeah, something that just like picks vertices, looks finite depth, does something with what it sees. And I go, okay, constant depth. Okay, that's it. Thank you.
Questions?
Yeah.
Can you say anything about non-uniform hypergraphs? Because it kind of feels like with your edge shrinking, right, you're already sort of considering non-uniformity anyway once you get past that first step.
Right, once you get past the first step. So I suppose it should, I mean, okay, assuming everything's kind of constant or about, like, then it's just about the initial conditions for the, so I think it should, yeah, if you came up with, yeah, that should. Now, how does that transfer to high girth? I don't know, because we really did only check for DK biregular bipartite graphs, like we checked the details, but now you change that to fixed degree sequence or fixed degree sequence by part type graphs, I don't know. Probably something's true, but we didn't do anything. Okay. Cool.
Is your local island, essentially it's a local thing, as like a little backtracking, right? You look ahead a little bit and you choose the best option or something like that?
Well, it's not backtrack. Every choice you make is like irreversible.
Okay, yeah.
But
But
you can pick it, you can look at some part of the remaining graph, look out at some depth, and say, I want to do something now. I want to pick these vertices. So you can imagine some other algorithms where maybe you pick a vertex, you look out to depth 10, and then you say, I'm going to take this one, this one, this one, this one, this one. Add all 5 of those to the independent set. You add these edges to the matching, whatever. You do something like that. But I'll just say that like this result basically says that, well, no matter what you do that's like that, you're not going to get an almost maximum independent set. You're not going to like hit the constant, right, for independent sets. And we don't know whether that impossibility thing is true for matchings yet. Probably is, but yeah.
And that, like, where you're going through the, like, steps, 1, 2, 3, you had D minus 1, D minus 2, and
Yeah.
so on, and then you blend it together.
Yeah.
Is there any, like, weirdness, like, at the boundary of the two blends, whenever you're, essentially, like, you might have, like, I'm gonna have an R, gonna be R regular, then R plus 1, and then R minus 1, and then sort of
Mhm.
oscillating between those three, or is
Yeah,
that?
no, it doesn't really happen because once these things start taking off, they're like linear in size. And they're very abundant, that means. So, okay, you do have to confirm with the numerical stuff that it never reverts to some previous phase. Because it's conceivable that like, oh, I started processing degree 3s, they started accumulating, but then like they just went down, and then I started doing degree 4s again. You know, that's conceivable, but the numerical solutions that never happens in any of the cases we checked.
Yes, thank you.
So we have to put in that thing like it never reverts to a previous phase. The phases always go forward like that.
Then let's thank the speaker.
Okay.
Break for lunch and come back at 1:30 for our third piece.